Okay, this is a solution to homework problem number 13-46. So, in problem 13-46, we are told that we have two concentric spheres that have the diameters of d1 equals 0.3 meters and d2 equals 0.6 meters, and where they're maintained at temperatures T1 equals 800 Kelvin and T2 is equal to 500 Kelvin. They have emissivities, emissivity 1 of 0.5 and surface 2 has an emissivity of 0.7. And it says determine the net rate of radiation heat transfer between the two spheres. So that's Q dot from 1 to 2 is going to be our question. And it says also determine the convection heat transfer coefficient at the outer surface if both the surrounding medium and the surrounding surfaces are at 30 degrees. So now we know that T infinity, or T of the surroundings, is equal to 30 degrees C. And it also tells us that the outer surface of sphere 2, I'll call that emissivity 3, is going to equal 0.35. And we are asked to find the heat transfer coefficient H. Okay. So let's try and draw what we have. We have a sphere within another sphere. Okay? And there is values. So this is sphere 1. This is surface 2. And we'll say the outside we'll call 3. So we have T1 was 800 Kelvin. The diameter here, D1, was 0.3 meters, and the emissivity 1 was 0.5. Then here we have surface 2, T2 is equal to 500 Kelvin, D2 was equal to 0.6 meters, and emissivity 2, 0.7. And outside of the outside surface, we have an emissivity 3, which is equal to 0.35. So the first thing we're asked to find is the heat transfer rate that goes between surface 1 to surface 2. So what is that? Q12. And then lastly, it says, what is our heat transfer coefficient? Or, because of the different emissivities, we'll be able to find out that the heat transfer between that leaves 1, because it's at 800, and radiates out to surface 2, okay, is also going to be able to escape. And that's going to escape in two ways. It's going to escape by radiation, and it's also going to escape by convection. Right, so we can have some natural convection currents. Okay. So if we do an energy balance at that surface, we'll notice that the Q dot from 1 to 2 is going to have to equal the Q dot leaving due to radiation plus the Q dot leaving due to convection. Okay, so we'll keep that in mind for part B of this problem. Okay. But the first thing we're going to do is we're going to have to try and find what Q dot 1 to 2 is. And luckily, the geometry of a sphere within a sphere is given to us in table 13-3. So table 13-3 tells us that if we have two concentric spheres, the heat transfer rate from 1 to 2 due to that radiation is equal to A1 times sigma times T1 to the 4 minus T2 to the 4 divided by 1 over the emissivity of 1 plus 1 minus emissivity of 2 over the emissivity of 2 times R1 over R2, and that ratio is squared. Okay, so that is, again, from table 13-3. So we'll start to plug in all of our values, and our surface area, A1, so the surface of a sphere, surface area is equal to 4 pi r squared, or this is equal to pi d squared. Okay, we'll use both of those. So we have 4 pi r1 squared times sigma t1 to the 4 minus t2 to the 4 divided by 1 over emissivity of 1, plus 1 minus the emissivity of 2 over the emissivity of 2 times the ratio of the radii, r1 over 2 squared. Okay, plug in. We have 4 times pi. R1 is going to equal 0.15. Square that. Sigma 5.67 times 10 to the minus 8. T1 is 800 to the 4 minus T2 500 to the 4, and we will divide that by 1 over emissivity 1, 0.5, plus 1 minus 0.7 divided by 0.7 times 0.15 divided by 0.3 squared. And we find that that is equal to 2,641 watts. So that is the answer to part A, the heat transfer rate due to radiation between the surfaces 1 and 2. So all we're left to do is find what that heat transfer coefficient is. So we'll have to start by finding out the radiation that escapes to the room. So we do that. We find that Q dot rad is going to equal the emissivity on that outer surface of the outer sphere times its view factor to the room times the area of that sphere, A2, times sigma times T2 to the 4 minus T of the surroundings to the 4. Okay? The emissivity of a sphere to the room is equal to 1. Everything leaving the sphere or the room can see the entire sphere, right? And then we have our area of the sphere is pi times d2 squared. That's the surface area of the outer sphere. So let's start to plug in our values. Our emissivity of that outer surface is 0.35. Our view factor of 1. Our area of pi times d of 0.6 squared, and times Stefan-Boltzmann constant, 5.67 times 10 to the minus 8 times the temperature difference, or T2, which is 500 Kelvin, raise that to the 4, minus the temperature of the surroundings, which we're given as 30 degrees C. So we'll change that to Kelvin by adding 273, and we will raise that to the 4th power. Punch this into our calculators, and we find that Q dot rad is equal to 1,214 watts. Okay. And when we did our energy balance on our surface, we saw that Q dot from 1 to 2 was equal to Q dot rad plus Q dot that leaves from convection. Okay. So we start plugging our values. We solve for Q.12, that was 2641 equals Q.rad 1214 plus Q dot due to convection. One equation, one unknown. Q dot convection is therefore equal to 1427 watts. Right? Then we can go ahead and turn to Newton's law of cooling that says Q dot due to convection is equal to H times the surface area, A2, times the temperature difference, which is T2 minus T infinity. And start plugging in. Q dot convection, 1427 watts equals H. A2 is again that pi times 0.6 squared times our temperature difference, 500 minus this value, the 30 plus 273, which is equal to 303 Kelvin. And one equation, one unknown. H is therefore equal to 6.4 watts per meter squared Kelvin. And that's it.